Good evening. Welcome back to AP Stats Notes Online. Want to start wrapping up Chapter 9. We've gotten through the basics and the details and the conceptual meaning of significance tests, type 1, type 2 error probability. What is the p-value? What is the significance level? And all that jazz. Power. We've talked about testing for population proportions. We need to extend that into testing for sample means. And the good news is a lot of things look exactly the same, just with some very small differences. And those differences come from the fact that we're talking about means and not proportions. So let's just sort of dig in here and get started. So what are the three conditions for conducting a significance test for a population mean? And so we're making the adjustment over to testing for means instead of proportions. Well, same as before, random data need to come from a random sample or randomized experiment. We haven't really talked about what that random condition check would look like if our data did come from an experiment. And we'll have an opportunity to do that through this section, probably not tonight, but tomorrow night. Right? Remember that your normal check is different. Your normality check, and again, you have to remember that the reason that we're checking the normal condition is so that our sampling distribution will be approximately normal. We'll know that our sampling distribution is approximately normal. Now, for sample means, the way that that happens is that either the population distribution is approximately normal, which, by the way, there aren't that many population distributions that are approximately normal, so it's not going to happen very often. Or our sample size is bigger than 30, and at that point the central limit theorem kicks in and tells us that our sampling distribution will become approximately normal no matter what our population shape is. So that'll help. Now, if our samples are smaller than 30, then we know that we're still in pretty good shape for our sampling distribution to be approximately normal, as long as our population distribution is not too heavily skewed or have any major outliers. And the way that we would know that is to take our sample data and plot it. And I won't go through all the details of the analogy, but it's kind of that thing where, you know, kids tend to look like mama, and the mama graph being the population distribution, right? So we're going to graph the kid, we're going to graph the sample data, because we know the sample data typically looks a lot like the population data. So and we're going to look for no heavy skewness and definitely no outliers. And as our sample size decreases and decreases and decreases, then we can accept even less and less skewness, and at no point do we want to see any outliers, because then we won't know exactly what the shape of the sampling distribution would become. So anyway, if your sample size is less than 30, then your check becomes to plot the data, and then we have to talk about the population distribution not having any skewness or any outliers, and therefore allowing our sampling distribution to be approximately normal. Okay? That's why we're doing that. And of course, independent, we want to make sure that our observations are independent in the sense of an experiment. And again, we haven't really seen an independent check when we're pulling data from a randomized experiment, and we will, but that will sound a little bit different than what it does for random sample data. Right? And so when we're random sampling, again, we want to make sure that we're not sampling more than 10% of the population. Okay? And that allows our standard deviation of the statistic to be a fairly accurate measure of that distribution. Okay? All right. So a lot of the same, and then we can get to our test statistics. So we've checked our conditions, and we're ready to start performing the test. Where does the test statistic for testing population means come from? Well, as you see here, we switch from talking about a z-score to talking about a t-score, right? We go from a normal distribution for our sampling distribution to a t-distribution, which is not really normal. It's different than a normal curve, and we haven't really explored how different or why, and we haven't really explored the different characteristics of the t-curve. We'll need to do that before the AP exam. We may even find a few minutes before this test to talk about that. I think it's important that we do that either before this test or before the AP exam. We'll definitely get it done before then. Okay? Anyway, our test statistic, and remember that in your formula packet, there is the general form of how to find the test statistic, right? And that's, we're going to take our statistic, subtract the parameter, and then divide it by the standard deviation of the statistic. Okay? For proportions, that means a z-score. Okay? For means, something weird happens when we start calculating the standard, or start using the standard deviation of a statistic to try to find this standardized value. And that weird thing that happens is that our curve looks a little bit different. It takes a little bit different shape. And the reason why is because of that guy right there, right? When we're using the sample standard deviation, okay, to standardize all of our sample means down, then it shifts that shape a little bit, okay? So again, I want to make sure we make that tie as to why we get into a t-distribution instead of a z. And it's all about having to use the standard deviation of a sample to standardize down instead of the population standard deviation. And if you're wondering why that is, it's because the standard deviation of a sample is calculated a little bit differently. You know, the first difference is, if you think way back to chapter 1 when we talked about standard deviation, if you go into the formula, we're finding an average of something, and I won't go through all of it, but we find the average by dividing by n minus 1, so 1 less the number of observations instead of the number of observations, which, if you're finding the average of something, would make more sense to do. Okay? And for that reason, and there's reasons for doing that even, but for that reason, the calculation for S is a little bit different than for sigma. So it does sort of affect some things, and this is one of the things that affects. So we're no longer in table A or a normal distribution, we're in table B or a t-distribution, and that's why. I want to make sure we make that tie. Okay? Now, we know that table B looks a little bit different than table A. So how do you calculate p-values using the t-distributions? Well, the short answer to that is we're going to use the table and the calculator, obviously. I mean, that's how we found our p-values for even when we're in a normal curve, a normal distribution. But to see exactly how, I think we just have to do one. So let's take a look at a couple of situations and start talking about how to find the p-values. So let's do some. First example, find the p-value for a test of H0 that claims the population mean to be 10 versus an alternative hypothesis that we believe the population mean is greater than 10. That uses a sample of size 75 and has a test statistic of t equals 2.33. So we've gone through the t calculation there, and our test statistic is 2.33. All right? Well, first thing I want to show you is the table. Right? So we bring up the table. Our sample size was 75. Therefore, our degrees of freedom, which we need to make sure we report to everybody when we perform our test, it's going to be 1 less that. This is going to be 74. So we need to go to degrees of freedom of 74. Degrees of freedom are over here. 74, unfortunately, is not listed. So we always, round down, right, to the next available line, which is going to be line 60. And then we look for our t to be 2.33. Well, we move over and look for 2.33. Well, there's not a 2.33. We actually, as a matter of fact, fall in between these two values right here, which is in between the upper tail probabilities of 0.01 and 0.02. Okay? So what do? Well, quite simply, we report a range of p-values in between 0.02 and 0.01. Okay? So what is that p-value? It's literally between 0.01 and 0.02. We don't need to get any more specific than that. Okay? So when using the table, we'll talk about a range of p-values. Now, using the calculator, okay, we can actually be a lot more specific. Right? We go into distribution, because the t is just a different distribution. We're going to use TCDF. It needs a lower bound and an upper bound. Now, because the table B uses the upper tail probability, and our test statistic was 2.33, so it fell somewhere 2.33. Our lower bound is going to be 2.33, and our upper bound is going to be something that will put us out in that tail quite a bit, so we can make it 100. And it does ask for the degrees of freedom. And so we're not going to type in 75, we're not going to type in 60. We're going to type in the actual degrees of freedom, which is 74. Okay? And you hit enter, and there is a more accurate p-value, 0.01127, okay, which is between 0.01 and 0.02, closer to 0.01. Okay, so if you get comfortable enough with your calculator, then you can start reporting p-values a lot more accurately. All right, so let's try this again. And this time find the p-value for a test where the null is mu equals 10 versus the alternative mu is not equal to 10. That uses a sample of size 10 and has a test statistic of t equals negative 0.51. Now think about what that means. It means whatever sample we gathered, whatever data we gathered, and we calculated the mean must have been less than 10 because the t is negative, right? Well, take a second and see if you can't think through that. Stop the video and see if you can't come up with it, and then check yourself. Okay, so what did you come up with? All right, well, two ways we're going to do this. We can use the table, and I'll do the table first. Negative 0.51. Well, let's look at what the table actually does for us. It reports area in the upper tail, okay? But a t-curve is like a normal curve in that it is symmetric. And so whatever the upper tail probability is here, the lower tail probability is going to be the same, and vice versa. So if we get a t-value that's negative 0.51, then we can just switch over and use the positive version of that to find our tail probability. And when we have our tail probability, we can go from there. So our sample size was 10. We need degrees of freedom of 9. And now we're looking for a t that is 0.51. And so we move over, and there is no 0.51. Okay? Which means that our tail probability is at least 0.25. It's at least 0.25. Now, here's the other thing you have to consider, is that our tail probability is at least 0.25. So far, our p-value, we have to say, is at least 0.25. But this is not a one-tailed, but a two-tailed test. And so we need both tail probabilities, right? An X bar that is as big as or bigger, larger or larger, as large as or larger compared to the claim, okay, also has to be considered. It's kind of weird to say. But anyway, it's a two-tailed test. We'll take larger X-bars or smaller X-bars than 10 to provide us our evidence. And so we need both tails. Again, it's symmetric. So if we have at least 0.25 in the upper tail, then that means we multiply this by 2. Our p-value is actually at least 0.5, okay? Which you see here, okay? So you had to multiply that p-value by 2. Now, it's not very accurate. It isn't. So we can get into the calculator, and I'll show you that real quick as well. Again, I'm going to sort of use the curve on the table to help me out here, but I'm going to do TCDF again, and this T star is going to be that positive 0.51 that I was looking for before. Okay? And then 100 is still going to put me out in that tail far enough. I've got to change my degrees of freedom to 9, because the sample size was 10, right? And hit enter. There you go. Now, that's just one tail. So I need the second tail factored in as well, so I'm going to multiply that by 2. And so the p-value is actually 0.622, which is at least 0.5. Okay? So remember, if we're doing a two-tailed test, we've got to multiply that p-value by 2. All right? Good. I think that gets us into just doing a test. Okay? So let's go do that. Every road has one at some point. Construction zones that have much lower speed limits. To see if drivers obey these lower speed limits, a police officer used a radar gun to measure the speed of a random sample of 10 drivers in a 25-mile-per-hour construction zone. Okay? And here are the results of those 10 drivers. Can we conclude that the average speed of drivers in this construction zone is greater than the posted 25-mile-per-hour speed limit? Do we need to monitor that zone a little bit more closely because people are driving too fast, right? You can use this in terms of an allocation of your resources, right? Do you need to post an officer there to get everybody to slow down? Well, let's go find out. Our 4-step process is in effect here. So state, what do we want to test? We want to test the null hypothesis is, again, it's that hypothesis of no difference. It's that statement of no difference. So we're going to assume that the average speed of all the drivers through that construction zone is actually 25 miles per hour. We're trying to find evidence for that average of being actually higher than 25 miles per hour. And we're going to do that at a significance level of 0.05. Okay? Now, because we're actually using mu in our hypotheses, we need to go ahead and define mu. Let everybody know what mu stands for here. And mu is the true mean speed of drivers in this 25-mile-per-hour construction zone. All right? No problem. I'm going to go through this pretty quick, so if you need to stop the video at any point to sort of catch up writing, make sure you do that. But we've seen all this stuff before. So that means we're ready to state our inference procedure. We're going to perform a one-sample t-test. Remember now, this is a one-sample t-test because we're using t as our test statistic for mu, okay? As long as our conditions are met, right? So, random. It was a random sample of drivers that was selected, okay? Normal. Well, we don't know if the speed of everyone that drives through there is normally distributed. We don't know what the population distribution of speeds is. And our sample size is less than 30. So, what we're going to have to do, we're going to have to plot the sample data. Excuse me. Okay, and look for any departures from normality. Again, from skewness and outliers. Okay? A dot plot works just as well as anything else does. There are only 10 speeds to plot out, so it wouldn't take you that long. You do have to show the graph. If you're ever in a situation like this, where your sample size is less than 30, you're going to have to show a graph. Okay? Now, if you get good enough with your calculator, the calculator will do it for you as long as you type in your data into a list. Then you can sort of copy over the graph that you get in your calculator, whether it be a histogram or a box plot, okay? But you're going to have to show it. Dot plots are pretty easy and pretty quick to create. Stem plots can be as well, but dot plots for sure are easier and faster. So we look at that distribution, and there's no skewness really. I mean, there's not really much of any peak there, so there's no skewness and probably no outliers. There is this guy down here at 21 that's sitting, but it's really not that far away from the center of this thing, so my guess is it's not an outlier. If we are really concerned about that observation point, we can always go determine if it's an outlier or not by doing 1.5 times IQR and subtracting from Q1 to see if we get there. It's not going to be an outlier. Okay, so since no skewness, no outliers, we're pretty safe to go ahead and use this procedure, right? And then last but not least, we've got our independent check. We're going to have to assume that there are more than 10 times 10 or 100 drivers that go through this construction zone, and that's probably pretty safe. Okay? All right, so our conditions are met. We're ready to go do the test. So you're going to have to find the sample mean. It wasn't given to us, but you have the 10 data points. You type them into a list and hit one variable stats in your calculator. And it'll give you the sample mean and the sample standard deviation, and here they are. Okay. Your calculator, if you type these into a list to create your distribution, the calculator will pull from the list to do the test when we get to using the calculator, and I'll show you that in class very quickly. Okay. So that we need that, we need to report that. So we need to write out X bar is 28.8 and S of X is 3.9. We need a test statistic, right? And so we're going to call it T. We need the statistic minus the parameter, so 28.8 minus 25 divided by the 3.94 divided by the square root of 10. This is your standard deviation of a sampling distribution for sample means. And again, you'll find a box on that third page in your formula packet that will remind you which standard deviation calculation goes with which test. All right. Anyway, our test statistic is 3.05. We need to turn that into a p-value. Okay. We just talked about how to do that. I'm going to leave it for you to go figure out what that p-value is. Okay. Now, or not figure out, but to verify, right? We can use a calculator here, and you should get a p-value of 0.0069. We sampled 10 drivers, and so our degrees of freedom is 9. Whether you use the table to give a range or use your calculator to give an exact, either way, we should get 0.0069. Or if you're looking at your table and you're wondering, we're going to have to report our p-value as between 0.01 and 0.005. Okay, which this guy, 0.0069, definitely sits in between. Okay. Now I'm questioning myself. Yeah, we did report our alpha. Good, it's up here at 0.05. And so now we're ready to conclude. Our p-value is most definitely less than alpha. 0.0069 is less than 0.05. So we reject the null hypothesis, which means, so that's our first statement. Our second statement's got to be about the alternative. There is convincing evidence that the true average speed of drivers in this construction zone is greater than 25 miles per hour. That being the case, we got to slow everybody down. And posting an officer there might do just the trick. So, anyway, given your conclusion in part A, which kind of mistake? And this is a very common follow-up question to a significance test. So, a good one here to put here. Which kind of mistake, a type 1 or type 2 error, could you have made? Explain what this mistake means in this context. Now, because we rejected H0, which type of error are we subjecting ourselves to? Hopefully you're thinking to yourself, a type 1 error. Now, if that's the case, what does it mean in context to have committed a type 1 error? That means that we have concluded that the mean speed of the drivers through the zone is greater than 25 miles per hour, when in fact it's not. It's equal to, right? And that's exactly what we see here. In other words, it is possible that we conclude that the average speed of drivers in this construction zone is greater than 25 miles per hour, when in reality it isn't. Okay? Which means we put a cop there for no reason. And that may or may not be okay, depending on the situation. Okay? But you've got to make sure you can talk about type 1, type 2 errors in context there. All right? Good. Take a look at one more quick example. Again, I'll get through this as quickly as I can to show you that there again is a tie to confidence intervals here as well. Right? So, you ever played the game Don't Break the Ice? I had never until I had kids, and we have that game now, and my two girls love it. Especially my 4-year-old, she just goes to town on those little cubes of ice with that little mallet thing. So anyway, if you haven't played it, there are these little cubes that you shove into a square, and there's a guy that sits on top of it, and you take turns tapping out the cubes. And the idea is to not be the one that makes the guy fall off the ice, okay, or fall through the ice. So, in order for that to happen, the cubes have to be big enough so that they hold each other in place, sort of squeeze each other in place, but also not so big that you can actually tap them out. So, the machine that produces the plastic cubes is designed to make the cubes that are 29.5 millimeters wide, but the actual width varies a little. To ensure that the machine is working well, a supervisor inspects a random sample of 50 cubes every hour and measures their width. The Fathom output. Fathom is another statistical software program. We have not gotten to work with Minitab nearly enough, and that's unfortunate. But again, I've always kind of had my eye on the schedule a little bit. So, but anyway, this is a Fathom output, right? And so what we're taking a look at is the width for the 50 cubes. The mean width is 29.4943. The count is that he checked 50 cubes. The standard deviation is 0.0877121, and the standard error is 0.0124044. Okay? If you take 0.0877121 and divide it by the square root of 50, you get exactly that standard error, 0.0124044. Okay? Now, a question we haven't come across yet, which is why I wanted to take a look at this problem real quick, was interpret the standard deviation and the standard error provided by the computer output. Standard deviation we ought to be able to interpret. We've done that before, right? On average, a cube's width will be 0.0877 millimeters away from the mean. Okay? Sounds good enough. Standard error is what we get when we consider a sample. And so standard deviation is talking about an individual in the distribution and on average how far away from the mean they're going to be. The standard error suggests that we have to talk about that in terms of samples. So in random samples of size 50, the sample mean will be about 0.0124 millimeters from the true mean on average. Okay? So every time we take a sample mean, that sample mean will be about 0.0124 millimeters from the true mean on average. Okay? Same type of idea for the interpretation, just interpreting in terms of samples instead of individuals. Okay? So the question, these data give convincing evidence that the mean width of cubes produced this hour is not 29.5 millimeters. Use a significance test with alpha equal 0.05 to find out. Okay? So we're going to do the test, and the key wording here is not 29.5. Not greater than or less than, because either way the inspector is going to care. So we just want to see if it's not equal to 29.5. Okay? And so we're ready to perform our test. Right? Again, a lot of the same things. State, your null should be mu equals 29.5, and the alternative is mu is not equal to 29.5. We're going to use an alpha of 0.05 and define your mu, the true mean width of plastic ice cubes. Okay? Now, we're going to perform a one-sample t-test. We need our conditions, right? The data is coming from a random sample of plastic ice cubes. We don't know if the size of the cubes, all the cubes, is normally distributed, but we do know our sample size is bigger than 30, and so central limit theorem says it's okay to use t procedures. Okay? They're independent. It's reasonable to assume that there are more than 500 cubes produced by this machine each hour. They're spitting out a lot of those games, and I'm trying to remember, I think there's 16 cubes in each game, so it's probably not unreasonable. Okay? Alright, so we're ready to go do. We need a test statistic, okay? And I'm not ready to relinquish the formula just yet, so do make sure that you show where your test statistic is coming from, right? We need a mean from our sample, which is 29.4943, minus our 29.5 all over. Okay, take a look there. All over 0.0877 divided by the square root of 50. Or if you wanted to, you could just write in 0.012 since we have that standard error given to us. Okay, and that test statistic is going to be negative 0.4595. And so now we need a p-value. And whether you get into table B or into your calculator, again, we're going to consider the positive version of t, just because we know that the curve is symmetric, right? And so you should be able to get to a p-value of 0.648, right? Now don't forget, this is a two-tailed test. So whether you use the calculator or if you use the table B, whatever p-value you settle on, you're going to have to multiply by 2, okay? So your p-value should be 0.648, which just reporting it that way is good enough. And so, and again, here's that reminder, 2 times the p-value, and you have to remember that your degrees of freedom, which should be written in here, it's in here as a note, but do make sure that you're reporting your degrees of freedom, which is 49, okay? But you have to multiply your p-value by 2, and that will get you your actual p-value, okay? Now, your conclusion. Since the p-value is greater than alpha, obviously it's a lot bigger than alpha. We fail to reject H0. What does that mean in context? It means that we do not have convincing evidence that the true width of the plastic ice cubes produced this hour is the true mean width, is what we should say. The true mean width is what we should say here. Is different from 29.5 millimeters. So what does that tell the company? Well, it tells them, you know what, it's okay. We're producing cubes that are okay sized. So keep going. Okay. Calculate a 95% confidence interval for mu. Does your interval support your decision from part B? Remember, since our significance level is 5%, the confidence interval that is tied to that is the 95% confidence interval. If you need a reminder as to why, make sure you ask in class, and we'll talk about that, okay? But, and I won't go through all of that process. I will say this. If you get a confidence interval as a follow-up question to a test, just to check your answer, all of your conditions have been met, right? So there's no sense in going through all of that again. As a matter of fact, you should be able to just report the interval and talk about if it supports your decision, okay? So when you create your interval, you should give it a shot real quick. You should get this interval here, 29.469 to 29.519. And to interpret that, we're 95% confident that the interval from that to that captures the true mean width of plastic ice cubes produced this hour. Now, what are we looking for? Well, 29.5 falls in the interval. So since 29.5 is in our interval, it is certainly a plausible value for the mean width. So we do not have convincing evidence that the true mean is not 29.5. I mean, it certainly may not be, but it very well could be. So, and this is the same conclusion that we made in the significance test earlier. So there is that link between confidence intervals and significance testing, two-tailed testing. Remember, it's got to be a two-tailed test before our confidence intervals seem to have that link, okay? So that's it. Like I said, a lot of the same stuff, just getting to a p-value is a little bit different, and obviously our normal check and the fact that we're using a t statistic instead of a z statistic when we're testing for a mean, okay? We'll stop here. Homework that goes along with these notes will be in the text. We'll see you guys next class period.